Hi folks, lesson 2. This one's on loudspeakers and headphones. It says at the top there it's physics only, so if you just switch to the combined you don't need to do this one, although I am going to put another one up for transformers when I get a chance, and that is just for higher combined, so when that pops up obviously give that a go. I'll share the outcomes with you in a minute. In fact, I've not put outcomes, I've shown you, I've got the spec on there, you can look at the spec. First thing I want you to do is look at these 3 diagrams on the starter slide. So these are the hand rules that we've looked at so far. So do you recognise them? What does each part show? Like what are the fingers doing on this one and the thumb? Same for this. What are the fingers doing? What's the thumb doing? What are they representing? And then obviously this has got 2 fingers and your thumb. What do each part of this diagram represent? What do they show? What do you use it for? Okay, so have a quick think about that. You can pause it if you want. Have a quick think about it, and I'll go through it in a second. Okay, right. So the first one then. So we've got the right hand grip rule. Okay, so I think this was the first one that we went through in the lesson. And what you need to remember about this is that your thumb points in the direction of the current. So this is for a single piece of wire. Your thumb points in the direction of the current, and once your thumb's pointing in the direction of the current, your fingers then show you the direction of the magnetic field. And you can see I keep doing this with my fingers. I want you to think about it like that's my fingers curling around, going round in that direction, showing you which way the magnetic field's going round as well. Okay, so that's the right hand grip rule. You've then got the second right hand grip rule, and you can see the difference between this one and the first one is that this one's for a solenoid, for a coiled piece of wire. The arrows there, as you can see them, along the solenoid are showing you the direction of the current. Okay, so the first thing I wanted to point out was that your fingers curl in the way that the current's going. Okay, so the current's going up on this side of the solenoid, so my fingers need to go up on that side of the solenoid. And once you've done that, your thumb's then pointing in a direction, and that direction shows you the magnetic field direction, and it's your thumb points north. Okay, remember they can give you these in context, like give you a question and ask you for a direction. Just because though I've told you to line your fingers up for the second right hand grip rule with a current, and your thumb then points north, they might say they might flip that. They might go, here's a solenoid, this is the north pole of the solenoid, and this is the south pole of the solenoid. Which way is the current going? Okay, it's the same rule. It's just that they're flipping which thing it is that they're asking you for. Okay, so in this situation, obviously that would be the north pole of the solenoid, and that would be the south pole. Remember, the magnetic field looks very similar to a bar magnet. In a bar magnet, obviously you've got the field emanating all around the bar magnet, whereas it does that on this, but it also passes through the centre of the coil as well. So in terms of what it would look like, it'd come out and round north to south, but then it passes through as well, and then north to south and through as well. Okay, so that's what the magnetic field lines would look like for the solenoid. And then this one is the left hand rule. You might see it called Fleming's left hand rule. It makes no difference, it's the same thing. What do you need to know about this? Well, you need to remember that your forefinger, this one, is meant to be aligned with the magnetic field, going from north to south, magnetic field. The second one, where your second finger has a C in it, and that's for the current. So second finger, you align that with the direction of the current. And it says there positive to negative, so assuming conventional current, but they'll either give you the direction of the current, or I suppose they might ask you to work out what it is. They might give you the power supply and show you which end's which is positive and which is negative, and then ask you to work out which way the current is. And then for the final one then, so your thumb on your left hand rule, that is the one that points in the direction that the conductor is going to move. So usually a piece of wire or whatever it is, your thumb will point in the direction that thing's going to move. They've put thumb's got an M in it for movement. I told you that thumbs starts with a TH and it's thrust. It's the same situation, isn't it? It doesn't matter which way you remember it, as long as you understand what that represents. There is one more to come. We're going to do that in school though, so that's going to be on the generators lesson, and we use the right hand for that. Okay, so there's actually going to be 3 associated with your right hand and 1 with your left hand, but they're all very similar. So as long as you've got an idea of a couple of them, you've covered most of the bases. Okay, right. So this is kind of in place of the outcomes. I've just lifted this directly from the spec. So I'll read it out to you. So loudspeakers, physics only, and it's higher tier only. So loudspeakers and headphones use the motor effect to convert variations in current in electrical circuits to the pressure variations in sound waves. Now we need to kind of link this, go back to the PE6 topic, waves, and we'll do that later on. But the idea is we know how to create a wave, a sound wave. So can we link that to electromagnetism? Well, we can, and that's what this is about. Students should also be able to explain how a moving coiled loudspeaker and headphones work. Now, I'm not specifically going to cover headphones in this because it's pretty much identical. It's just on a much smaller scale. So as long as you understand how a loudspeaker works, you inherently know how headphones work. Okay, so we'll just jump straight into it. Right, so let's have a quick recap because this topic's got a lot, isn't it? A lot in it. So it's quite busy. So let's have a recap. So the key things that you need to remember. So two magnetic fields in close proximity create a force. You've played with magnets and you know this. Look at the diagram at the bottom there, the animation on the bottom left. So you can see that opposite poles attract and like poles repel. They've put same poles repel, same thing. That force can either attract or repel, depending on the field polarity. So when we talk about magnets, that is, two magnetic fields interacting can either attract or repel. And you can see there, opposite poles attract and same poles repel again. Magnetic materials, and there's the list there, so iron, nickel, cobalt and steel. Remember, steel's only magnetic because it's got iron in it. It's like a high proportion of it is iron. They can only be attracted by magnets, not repelled. Look at the paper clips there and look at the magnets. The paper clips are being attracted to the magnets. If I turn that magnet around, like if I've got the magnets holding down like that. If I turn the magnets around and held them down, the paper clips would still be attracted because it's a magnetic material. It's not a magnet. Okay, so the iron doesn't have its own magnetic field around it. It's just attracted to the magnetic field of the magnet that's being held close to it. Okay, so magnetic materials can only be attracted. You can't repel a magnetic material. So electromagnets have magnetic fields that can be turned on and off. And we've looked at the field around electromagnet. Remember we made a solenoid, didn't we? We put it on a piece of cardboard and we got a compass and we held it at each end and then we passed it through and you could visualise, hang on, this looks a lot like a bar magnet. There's not much difference between it, apart from the fact that obviously you turn the power supply off, the magnetic field goes. So you can turn on and off electromagnets, which makes them hugely useful. A wire carrying a current generates a magnetic field around it. So we've looked at this in a couple of different situations where you've had a piece of wire that we connected into a circuit. I don't know if you remember this actually. And we had a piece of cardboard. We put the wire through the cardboard like that. And then we tied a knot in the wire to keep the cardboard up. And we put compasses around the wire. And then obviously we connected that to one side of the power supply and connected this end to the other end of the power supply. So each terminal, and we passed the current through it. And when we turned it on and off, you saw the compasses align around the wire, showing that the wire itself has a magnetic field as long as there's a current passing through it. You turn that current off, you turn the power supply off, the current stops, and then the magnetic field disappears. It's not there anymore. The field around a wire or a solenoid can be reversed by changing the direction of the current. So imagine that setup again where I've got my piece of wire and the magnetic field, let's say the magnetic fields go around clockwise. If I was to take the wires out of the power supply, unplug them, and swap them round and plug them back in again, well, if it was going clockwise before, it's now going to go anti-clockwise. So I can reverse the magnetic field around a conductor that's carrying a current. I can reverse that by changing the current direction. The magnetic field then changes as well. And we did that with the right-hand grip rule, didn't we? If the current's going up, then the magnetic field goes around like that. But if the current's going down, the magnetic field's now going round like that. Okay, so we can reverse magnetic field direction in a conductor by reversing the current direction. Okay. So this is the link that we need to make back to the P6 topic about waves. Okay, so you can see there's a nice little animation down there. And key things to notice are these. The peaks and troughs of this wave. So you can see there's a peak there. I don't know if you can see my cursor very well there, but there's a peak there and you can see it's travelling across the animation. So the peaks and troughs of the wave are due to areas of high and low pressure. And remember the key terms, compressions and rarefactions. Okay, so this here, that's scooting its way across the animation, that is a compression. And this bit here in between those two compressions, and there's another one there, and there's another one there, they're rarefactions. So that's an area of low pressure because there's fewer particles there. Way back in year 7 we did pressure. The idea that particles colliding create forces with every collision. And that's pressure, isn't it? Okay, the amount of force per unit area. And obviously if there's less particles, there's less forces, so there's less pressure. So when there's more particles, there's more forces being produced, and therefore there's more pressure. Areas of high pressure are created when particles are pushed closer together. So just look at this. Where this, whatever this material is moving backwards or forwards, it squashes or compresses that area of air, and those particles end up closer together. Okay, so we've got that happening there where it creates high pressure. Areas of low pressure are created when the particles are spaced further apart. So as the material there moves backwards, I'll do it this way so it kind of lines up with your screen. As it moves backwards, there's an area in front of it where there are now fewer particles. It's just pushed them closer together and now it's moved back. Think of it a bit like one of them coin pushers. You might have seen them in an arcade before. It pushes the coins forward, and then when the pusher comes back, there's less coins there where it just was, because, well, it's just emptied that space, hasn't it? It's just pushed some particles away from it and then moved back and created an area of relatively low density in terms of particles. An oscillating material creates these areas of high and low pressure, so that's what I've just said there, and you can see this red material here oscillating backwards and forwards. This is another nice animation where it's got the dots to represent the particles. Notice that the particles are oscillating as well. They're moving backwards and forwards, but the particles themselves aren't carrying the energy from one end of the wave to the other. They're colliding with other particles and transferring that energy, passing it on. Okay, so this is an acoustic longitudinal wave, acoustic relating to sound, and it's a longitudinal wave because the energy is parallel. The energy is travelling parallel to the direction of the particles. So particles are doing that, and the energy is running in the same plane, isn't it? Which is opposite to a transverse wave. This wave here as well has been translated into what looks like a transverse wave. We call this a trace, a wave trace. And you can see that the peaks of the wave are representative of the compressions of the longitudinal wave, and then the troughs of the wave are representing the rarefactions of the sound wave. Okay, so you can hopefully you can see where this is going. Okay, we can link the idea of moving something to creating sound waves. Well, this lesson is about loudspeakers and headphones. How can we make something move? Well, let's have a look. So this is the kind of diagram that you'd see on Bite Size. I might have even got this from Bite Size, I can't remember. There's not much to it. Like it's a pretty simple diagram. So we've got a magnet here, permanent magnet. This looks confusing, like it looks like a letter E, but what it actually is, if you was to see this in person, it's like a circular outer portion of the magnet, which would be the south pole in this case, and then there's an inner portion of the magnet, which would be the north pole in this case, and then the coil kind of sits inside it. I can't think of a good example to represent that right now, but it doesn't matter anyway. So you can see that we've got a permanent magnet, so there's a permanent magnetic field there. We've got a coil of wire sat inside a permanent magnetic field. I wonder what would happen if we passed a current through that. And then we've got a speaker cone, and obviously there's some arrows on there. So we want the speaker cone to oscillate. If we get it to do so at the same frequency as the sound we desire, it will produce that sound. Now, cast your mind way back to year 8, I want to say, when you did the ear, the structure of the ear, and how sound is converted from moving air particles to electrical signals that are being passed to your brain and then interpreted as sound. If you get your eardrum to oscillate at a certain speed, then you hear that sound at that frequency. So how are we going to get your eardrum to move at that frequency? We're going to get particles of air to hit it at that frequency. And how we're going to move those particles of air? Welcome to loudspeakers. So if we pass a current through the coil, it will move either forwards or backwards. I'm not going to ask you to use the left-hand rule to work out what direction this is going to move. It's not really relevant. I just want you to know that if you pass a current through it, it will move one way. Let's say it moves forwards. And then if I reverse the current, the field reverses, so the movement then reverses and it goes backwards. So I can make it go forwards and backwards and forwards and backwards. If you switch the current, this is just a worked example if you like. If you switch the current 100 times in a second, that means it'd go forwards and backwards 100 times every second. Forwards and backwards 100 times every second. Well, we've just created an oscillation. So we've just created a sound wave with a frequency of 100 hertz because it's moving backwards and forwards 100 times every second. So this is it in an animated version. And again, I've tried to keep this as simple as possible. A, B, and C. Well, what are they? Look at the diagram there on the left-hand side. That's just a static diagram. What is each part? Well, A is the cone. You might see this called a speaker diaphragm. Try and remember your own diaphragm under your lungs. The fact that can move up and down. Well, look at what that's doing. It's moving up and down. We've then got B, which is the permanent magnet, and you can see that's just like a ring. And then we've got the coil of wire that's wrapped around this. So this has got a core. The core is then attached to the diaphragm. This is all assembled, glued, adhesive, they're stuck together, however they want to do it. And when it moves down, it pulls the diaphragm down with it. And when it moves up, it pushes the diaphragm back out again. And look at how that's being achieved. All that's being happening here is the potential difference is flipping. So because the current's flipping, every time the current flips, the field flips, the direction flips. So we can then make this speaker move up and down, oscillate at whatever frequency we want. We just make that current change at the frequency we want the speaker to oscillate at as well. And again, very, very similar for headphones. Okay, so headphones, the only difference is this is happening on a much smaller scale. You've seen some speakers, you can get absolutely enormous. Huge diaphragms, huge coils, big magnets in them. obviously that's not happening in a headphone. Okay, in a headphone, it's the same structure, but it's just on a much, much smaller scale. And that allows us to hear sound, however we want to do it. Right, so there's a quick task for you I want you to try here. So there's a diagram there. Again, this looks quite complicated, but the parts are pretty obvious if you look at the terms at the bottom that I want you to use, the keywords. So label each part of the speaker diagram, and then this bit over on the right hand side, the sequence of how a loudspeaker works. Try and put these in order. Okay, so pause that for me, give that a quick go, and then I'll go through the answers in a second. Okay, let's go through that then. So we've got current, coil of wire, magnet, diaphragm, and frame. If you're unsure, do the ones that you know first. So this here is attached to this, which is attached to the coil. So this must be the diaphragm there. So diaphragm. Okay, that's that one done. Now this looks like a coil of wire to me, so I'm going to put coil of wire in there. Coil of wire. So we've done diaphragm, we've done coil of wire. This big structure back here, the one that looks like a letter E, they're not always going to look like a letter E, it just happens to look like one. That's the magnet, isn't it? So magnet. Forgot how to spell for a moment there. So magnet's done. So now we've got frame and we've got current. That's interesting. This must be the frame on the outside. It's what's holding, because the diaphragm is actually attached there to the frame. Because obviously we want it to be anchored in one spot, otherwise it'd just be flopping all over the place. We'd get a poor quality sound then. So that'll be the frame. And then let's see if we can work out why this is the current. Are they both current? The current's obviously passing through the wire. They must both be current. Yeah, okay, got both current, we'll take that. Okay, have we missed anything out there? I don't think so. So they're not going to ask you to do all this, to work out a direction of this. What you find is with this stuff, the triple stuff specifically in the electromagnetism topic, the questions seem to be quite simple on exams, because the actual, just the basic concepts can be pretty complex. So they're not going to go out and ask you to start using the left-hand rule and predicting current directions and coil movements and all that jazz. They'll be asking you questions of just like, how does it work? And, keeping it dead simple. What does each part of it do? How could you produce a sound of a certain frequency? Stuff of that nature. So it's not going to be anything that's too complicated. They're just going to try and keep it basic. Okay, so for these on the right hand side, we'll keep you here in the mic. For these on the right hand side, put the following events in order. Right, so the coil is attached to the diaphragm, so the force moves the diaphragm. The movement of the diaphragm moves the air particles, so the sound waves are produced. An electrical signal is generated. That sounds like number 1 to me. The current flows through the coil. Probably number 2. Since the coil is in a magnetic field, this generates a force. Okay, so I reckon an electrical signal is generated as number 1. The current flows through the coil as number 2. Since the coil is in a magnetic field, this generates a force. Because bear in mind, the current flowing through the coil produces a magnetic field around the coil. Around the coil. The coil's sat in a permanent magnetic field anyway, so now we've got a force being generated, haven't we? And if you're not sure why the magnetic field around the coil produces a force because it's in a magnetic field, strip it right back. If you've got 2 magnets and you hold them near each other, you feel a force because you've got one magnet in the magnetic field of another magnet's magnetic field. Well, we've got 2 magnetic fields here that are very close to each other, so it's the same principle. Right, so what's coming after the magnetic field generating a force? The coil is attached to the diaphragm, so the force moves the diaphragm. That sounds like right, yeah. And then the movement of the diaphragm moves the air particles so that sound waves are produced. Job's a good one. So we've just described how to produce a sound wave using electromagnetism. So maybe if you've got a broken speaker now, you'll be able to figure out how to fix it. But there's not much to it, realistically. Magnet, coil of wire, diaphragm. You've got those 3 things, you got yourself a speaker. If you've ever messed around with any speakers, especially like car speakers, especially, so I don't know why you might have adjusted one or put one in a car or something. The magnets on them are really, really strong, and obviously that's related to the force that we want to produce. If we're able to move these backwards and forwards more, we can get a bigger amplitude. We can make the sound louder, which obviously some people are obsessed with, making the speakers as loud as possible. Right, there's a quick exam question for you there. 9 marks, so aim for the 9-minute mark, obviously. 1 mark per minute. Give those a quick go, and I will give you the answers in a minute. I'm not going to put this separate as a worksheet, as a Word document, I should say, on Google Classroom. I'm just going to keep it on here this time, and I'll give you the answers in a second. Okay, so answers-wise, there you go. I'm not going to read through those. You can see what the answers are. Remember, when you're marking this, the 6-mark question, decide which level you sit in first. Okay, so read this, and read this, and read this, and that. I hope no one's on the 0 mark. But read those 4, then read your question, then come back to this and decide, right, do you reckon you're a level 1, a level 2, or a level 3? And once you've got to that point, you can then go, right, well, if I'm a level 2, for example, let's say you think you might be a level 2, am I getting 3 marks or 4 marks? This is when you then come down to the indicative content. How much of this have you included? Have you missed big portions of it out, important portions? Then you're probably on the bottom end of that level. If you've got most of it, then you're probably on the top end. You might even have marked yourself lower than you should have done. You might be touching onto the next level, okay? But be honest, give yourself a mark, and obviously there's the marks. Okay, if you've got any questions, that's going to be it for this. Dead short. If you've got any questions, again, drop them on either Google Classroom or put them on the YouTube video. Either way, I don't really mind. And yeah, that's it. I'll stick up the next one when I get a chance, which is going to be on transformers. There's an equation on the transformers lesson that we need to use. It might be worth you having a quick look at like a free science video again, like as a bit of pre-reading. But I'll put that up when I get a chance. And yeah, that'll do for today. See you later.